Hello students, we have discussed first case of electric field intensity due to an electric dipole on axial line. Now we are discussing case second when point P lies on equatorial line. When point P lies on equatorial line, just I have mentioned in previous topic that equatorial line means a line perpendicular to the axis of electric dipole, and passing through the center of the dipole. That line is known as equatorial line. Let us suppose here is minus q charge, here is plus q charge, and both are placed at a distance 2d apart. As I have mentioned earlier that we have taken the distance as 2d. This is the center of the dipole. O is the center of dipole. This point is A, this point is P. Both the charges are placed like this. This is A point, this is B point, here is minus q charge, here is plus q charge. And the distance between these two is 2d. This is center O. And a line perpendicular to the center, or line passing through the center and perpendicular to the axis of dipole, which is AB. AB is the axis of dipole. A line perpendicular to the axis of dipole and passing through the center is known as equatorial line. Now let us suppose here is any point P. At that point P, we want to find out electric field intensity. At point P, we have to find out electric field intensity. We know that at this point there is a unit positive charge. Therefore, if we consider these two charges minus q and plus q as source charges, then at point P, the direction of electric field due to both the charges will be different. I am drawing the diagram. Here is minus q charge, here is plus q, or we can say unit positive charge. Therefore, electric field intensity due to this charge will be in this direction. This is EA. But this is plus charge and this is again unit positive charge. Therefore, direction of EB will be like this. This is the direction of EB. EA is in this direction, EB is in this direction, and the point P is on the bisector of this line. Therefore, both the angles will be equal. Let us suppose this angle is theta. Therefore, this will be also theta. This angle will be also theta. Now I am drawing one line just parallel to AB and passing through point P. This line I am drawing here. This line we have considered as parallel to AB. Let us suppose this point is N. So now since PN and AB are two parallel lines, this angle is theta, therefore this angle will be also theta. And at point B, the angle is theta, therefore at point P, this angle will be also theta. And now after obtaining these two angles, we can easily resolve these two vectors in components, perpendicular components. This vector is EA. This is making an angle theta with PN. Therefore, component of EA along this direction will be EA cos theta, and component of EA along this direction will be, I am mentioning here, EA sin theta. This component is EA sin theta. Similarly, we can also find out component of EB. EB is making an angle theta with PN. Therefore, the component of EB along this direction will be EB cos theta. It means along this direction there are two components. One is EA cos theta, other one is EB cos theta. Along this direction, perpendicular direction, the component of EB will be EB cos theta. This is EB, no, this is EB sin theta. EB sin theta. Component of EB along perpendicular direction will be EB sin theta, and here it is EA sin theta, and these two components are EB cos theta and EA cos theta. Now let us suppose distance of point P from the center is R. As in the previous part we have also discussed distance from the center. This is R. Since this distance is R, this is D, therefore this distance will be root over R square plus D square. That is P. Now we are writing the value of EB and EA. Electric field due to plus Q charge at point P and electric field due to minus Q charge at point P. Now EB can be written as KQ divided by distance is BP. KQ by BP whole square. Or that can be written as KQ by R plus D root whole square. Or that can also be written as KQ by R square plus D square. This is the magnitude of EB. But the direction of EB is along P to M. Therefore, we have to mention along PM. This is the direction of EB. Now, here charge is minus Q. This is point P. At point P, again we have to write the expression for electric field, and that is for EA. EA equals to. Now EA can be written as KQ, and distance between this and this is AP whole square. Or that AP can again be written as KQ by root over R square plus D square and whole square. And therefore it again becomes KQ by R square plus D square. It means if we see this, it is clear that their magnitude are same, their magnitude are exactly same, but the direction is different. This is along P to A. So from these two expressions, it is very clear that EA and EB both are having same magnitude. We can write magnitude of EA equals to magnitude of EB. It means both are having same value, only the difference of direction. Now we have discussed the different components of EA and EB. Here in this direction the component is EA cos theta, one component is EB cos theta. In this direction one is EB sin theta and other is EA sin theta. So since EB and EA both are having equal magnitude but opposite in direction, here EB sin theta, EA sin theta, both components will have same value but exactly in opposite direction. Therefore EA sin theta and EB sin theta will cancel out each other, and therefore the net electric field at point P will be the sum of EA cos theta and EB cos theta. Again I am repeating, EB sin theta and EA sin theta will cancel out each other. Being equal in magnitude, opposite in direction, they will cancel out each other, and therefore net electric field at point P will be the sum of EA cos theta and EB cos theta. And this net electric field is known as E equitorial. Therefore, E equitorial equals to. EA cos theta, these are the components, plus EB cos theta. And along P to N, the direction is along P to N. The direction is along vector P to N. Since EA and EB both are equal in magnitude, therefore we can also write 2EA cos theta. And now we can put the value of EA and cos theta. Now it is 2EA. EA we have already written KQ by R square plus B square. And now cos theta, from this triangle, here it is base, this is hypotenuse, this distance is 2D, therefore OB will be D and hypotenuse is PB. Therefore we can write D by root over R square plus B square. And again direction is same, along PN. So it means 2KQD divided by R square plus D square, and again root over R square plus D square. Now in the final expression we want to use the concept of electric dipole moment. And since electric dipole moment is given by distance into magnitude of charge, it means 2QD. Out of this expression 2Q and D can be written as P. But if we see the direction of net electric field is Pn, direction of vector P, that is electric dipole moment, is from A to B. Therefore if we write 2QD as P, then final expression becomes equatorial equals to minus Kp by R square plus D square power 3. We have replaced 2QD by P, and direction of P and E are opposite. Therefore we have to mention one minus sign, minus Kp divided by R square plus D square power 3. So this is the formula for electric field on equatorial line of an electric dipole. But since the distance D is very small in comparison to R, the distance between two charges is very small in comparison to R, therefore R square plus D square will be nearly equals to R square. It means D square can be neglected, and in that case equatorial can be written as minus Kp divided by RT. In this expression we have assumed that R square plus D square nearly equals to R square. It means we have neglected D square. So this is the final expression for electric field on equatorial line. This is equatorial line, and here electric field is in this direction. Now in first case we have discussed that E axial is 2Kp by RQ. We can recall that E axial equals to 2Kp by RQ. E equatorial equals to minus Kp by RQ. Therefore we can also write relation between E axial and equatorial. Since E axial equals to 2Kp divided by RQ and E equatorial equals to minus Kp by RQ, therefore we can write E axial equals to minus 2 E equatorial. So this is the relation between electric field on axial line and electric field on equatorial line. And from this relation we can also find a very important question, that what is the angle between electric field on axial line and electric field on equatorial line. And from this it is clear that both the vectors are directed oppositely. Therefore, angle between E axial and E equatorial will be 180. So this is what about electric field on axial line and equatorial line due to a